Let's talk about conservation of angular momentum. And so here, for any isolated system, okay, we have no external torque, right? Remember, isolated just means there's no outside forces. In the case of rotation, that means there's also no outside torques. And that means angular momentum is conserved. So an isolated system could just be somebody at a spinning object on a playground. This is my friend Adam. He's going to demonstrate for us because he's a long, skinny person, so he can get his moment of inertia to change significantly. So we know, even though this is the same system, right? We're not adding or losing any mass, and we don't have any external forces. Once it starts spinning, you can change the angular momentum by changing the moment of inertia. So in this case, he's changing his moment of inertia by changing his position. He's like a really ungraceful figure skater, okay? So if you think about making a bike turn, falling off your bike, bringing your arms in to spin faster, all of those things are conservation of angular momentum. So remember, we have, just think I have to start by, no. Okay. So you hold this way. If I stand on here, I don't move. What happens if I flip it over?
You start moving.
I start moving. Which way? The same direction or the opposite direction?
Same.
Let's try it.
Oh,
Am I spinning the same direction as the wheel or the opposite direction of the wheel? Now why is that? Okay, so remember it's a vector. So when I spin this thing this way, it actually has an arrow so you can see it. So if I spin this thing this way, which way does the angular momentum point? We use the right hand rule. Okay, so you curl your fingers in the direction of motion. So we curl our fingers in the direction of motion. Which way does the angular momentum point? Towards you guys, okay? So if I flip it up, that means my angular momentum points up, okay? So let's say I have an angular momentum, let's call it just 1, okay? If it goes from 1 pointing up, if I flip it over, what is it? Negative 1. But we know it has to stay the same. So what has to happen? What am I doing? We have 1, negative 1. What do you have to add to negative 1 to get back to 1? 2. So that means I need to have positive 2. Okay? So when I'm spinning this way, if this thing's spinning this way, right? That means I have to start spinning the opposite direction to cancel out this change in angular momentum. So we have a constant angular momentum. Okay? Because this is an isolated system and angular momentum has to be conserved. And that's where the vector comes in, because we know that the vector points up. If we flip it around, right, now it's pointing down, and that means I have to create another vector that points up and is larger to compensate. Okay? Cool. Okay. We're going to try this one out. I will work through this with you, but we have 2 masses at the ends of a 50 centimeter rod. So you basically have 2 points way out here, okay? The rod spins at 2 revolutions per second about the center, and we can expand the rod out to a length of 160 centimeters, and we want to know the rotational frequency after the expansion, okay? So do you think this thing is going to go faster or slower? Slower. Why do we think it's going to go slower?
Because moment of inertia.
It's longer, right? So the moment of inertia is bigger, okay? So we're going to try this out. Okay, I don't know why I did that. We have 2 masses, and here's our initial configuration. We'll call these M. And our radius, this is our center of rotation, and we have a radius of 0.25. So this is a 50 centimeter. Then at a later time, we have a much longer broad, same masses, and this becomes 160, so 1.6 meters. Okay. Okay. So we know that what we're doing is conservation of angular momentum, which means that we have I initial, omega initial, I final, omega final. How do we calculate the moment of inertia for this? What's the moment of inertia for just a point? Yeah, mr squared. Okay. So what's r in this case? Let's call this length. This is length initial, and this will be length final. So we can write this as I initial is going to be 2 times the mass times L initial over 2 squared. Okay, we okay with that? Okay, and then the moment of inertia final is going to be 2 times M times L final over 2 squared. Okay, so we're going to plug these in. This becomes 2M L initial over 2 squared omega initial, and this becomes 2M L final over 2 squared omega final. We can do a lot of canceling. So 2's go away, M's go away. You can actually get rid of these. So you end up with that's weird. L initial squared omega initial is equal to L final squared omega final, and we can solve for omega final. Oh, actually, do we want to, we can plug in frequency first. Yeah, let's do that. Then we don't have to convert. So L initial squared, this is 2 pi frequency initial. L final squared times 2 pi frequency final, and then we can get rid of the 2 pi. So our frequency final should be L initial over L final squared times frequency initial. We did all this symbolically because there's a lot less math involved when we actually have to plug in numbers, so that makes it a little bit easier. So the L initial is 0.5 meters and L final is 1.6 meters. We can square this, and that's times 2 revolutions per second. So remember, do we expect this to be getting bigger or smaller? Smaller. So once we plug it in, then it gives us 0.195 revolutions per second. We have it in frequency instead of angular speed, just because that's what the problem asked for. So remember, for moment of inertia, if we just have a point, it's just m times the distance squared or the radius squared. For objects that are in the chart, we can look it up. For objects that are in the chart but not at the center of mass or at the edge, we can use the parallel axis theorem. And for objects that are outside of all of those things, we'd have to integrate the moment of inertia. Okay. Conservation of angular momentum is pretty straightforward. It's just keeping track of all of the pieces and making sure you get the numbers correct and the signs correct because it is a vector. All right. Okay. That's pretty much the end of that chapter.